So this is capsule 3 for Calculus 1 at John Abbott College. So I'm explaining everything, all the concepts that we covered in the unit 3 of calculus for this video. There was unit 1, there was unit 2, this is unit 3. So the first unit is all about limits, second is all about derivatives, and third is all about integrals. And in our program, I'm only explaining stuff that we learned in John Abbott because the whole point is to show what we learned. It's because it was something that I wanted to get when I was starting CEGEP, before I was starting CEGEP. And there are a few stuff that are in Cal 2 that are transferred to Cal 1 and vice versa. So there might be stuff that are not covered in my program that will be maybe covered in yours, or that we cover more than other CEGEPs, but I think they're all basic and they're all really easy. Everything that was in Cal 2 that was transferred to Cal 1 is the basic of integration. So we're gonna start off with optimization. Actually, it's like a continuing of situational problems from related rates, but right now, instead of related rates, we're talking about optimization. I'd say that's really similar, but it's also typical in the terms in the context that it will only matter for when whatever f prime you found is equal to 0. So you're going to be given a situation with a function. They will give you a function, and you want to turn that function into a derivative, or like a slope function. So the derivative f prime function, you turn that into equal to 0, and you just have to find whatever points x there are that will apply to that function being equal to 0. So let's say x to the 2 plus 4x plus 6, that was what you got, and you want that to equal to 0, you look for what x's are. It's really that simple. But to reach this, to turn your situation into a function, into a derivative function, there is a few obstacles you have to usually go through, and that's all about substituting. You're substituting or replacing one value into another to by algebra. So to make only one unknown. You always want only one unknown, and that's the key to doing optimization. So that's, did I spell that right? Optimization, yes. Optimization for, let's say there's a cube. This is a very typical question, and the one that was similarly on the final exam. So there's a cube, and you're given, not a cube, but a square prism. There's a y, and there's x's because the base is a square. Oh no, the base is a square, and we're asked what is the dimensions x and y of this box, so that the volume is maximized. Maximized means the volume is as big as it can possibly be for a rectangular or like a square prism. And we are also told that the area has to be always 300 centimeters squared. So there's usually one condition, that's the condition, and one demand, or whatever they're asking for. So in here, we're going to have, actually there's also other data they're going to usually give us. Well, in here we don't need more than this much of information because we can see it by our eyes, but the area, this area means 2x squared plus 4 times xy, because xy is like the walls, and the x squared is the base, but there's 2 of that, so area is equal to 2x squared plus 4xy. And when I was saying substitution, that's what I mean, because if you substitute, let's say because there's squares on the x's and there's only one y, it's easy to substitute y. Area, we know that has to be 300. 300 is equal to 2x, so 2 plus 4xy. If you want to isolate y, minus x, so 2 divided by 4x is equal to y. Now we have a new expression that will replace y, and that is exactly what we want. we want this. We want this so that we can plug y into a function so that the function will only have x's as the unknown. Because remember, we only want one unknown. That's the key to doing these optimization questions. The final, it was like a cylinder, and we had like the discs and the rectangular wall that we have to consider into the calculation, and we have to maximize I think it was the area, no, the volume. Have to maximize the volume or something, and it was quite confusing because there's like so many components. But try to always bring it down to one unknown. By doing that, you will just get it right. There's no way you will get it wrong. So right now we have volume that we want to maximize. So whatever that we're supposed to maximize or minimize is the function that we're going to derive. So v is equal to, we know that it's base times height, or base, or the area base, so x squared times y, that's our volume function. And we know that y is this big expression, so just rewrite it. There's nothing derived over here. Rewrite your expression, 2. And then we're gonna distribute the x squared here. And now, well, actually we can simplify even further. Just simplification is really helpful. So just let's simplify. This can turn into 150 x minus 3 over 2. So now is the time to derive. We can make v prime equal to, set equal to something. And remember that we want to make v prime equal to 0. Because optimization is all about turning your f prime, the new function that we found, f prime, set it equal to 0. So if you derive this one right here, well, we know that 1/2 is just a constant. Treat it as a constant. And the inside is 3, well, minus 3x to the 2 plus 150. And we want to set that equal to 0. So it's just simply that has to give it 0. So minus 3 equals to 2 plus 150 is equal to 0. Or we could just say that is equal to 0. X is equal to 150 divided by 3, so that's a 50. But then it's rooted. But then don't forget your plus or minus. Always remember your plus or minus. X is equal to plus square root of 50 or minus square root of 50. But we know that this has to be rejected in this problem because a negative x value, a negative measurement does not exist. So we know that the answer is positive root 50. You don't even need to write the positive root. But that's for x. X is equal to that. So we can also look for y by using either this one, or you can do the complicated stuff and go look for that. But I'd say you can just plug in here because you already have y directly. So 300 minus 2 times root 50 divided by 4 times root 50. And you can solve for y, which gives root 50. That is the optimization. It's the same thing for all the other questions. You're just setting a function. You're going to look for the prime of that function, set it equal to 0. And if it is a fraction, you want to set it equal to 0, meaning the top has to equal 0. So you don't need to care about the denominator. If, on the contrary, you're looking for when the function is d and e, then you're looking for when the bottom is equal to 0. But usually in our calculus course, at least, we didn't have to look for when the function or the prime function was d and e. And the simple reason is that we want when the function or the slope is equal to 0, not really where the slope does not exist when it's like that. This is when the slope does not exist, right? Because it's a corner. A corner like this does not exist for a slope because the slope will be either this one or suddenly equal to that one because it's like a pointy curve. So like that's the slope for this side, and then suddenly that's the slope, and basically the slope and this at the center does not exist. Here the center does exist, but is equal to 0. That's what we're looking at. That's what we're looking for. And optimization is about maximizing or minimizing, meaning when the function is the highest or the lowest. That's what we're looking for. It could be like, oh, when is the volume maximum? When is the cost of the lowest, so the minimum? And that's usually when the function is 0, not when the function does not exist. So that's not really the case that we're going to be looking at. A few more that I was kind of tripping over is when they gave us a point and they told us to find a point on the function. Let's say the function was f of x equals to root x, where it is the closest distance to the given point for 0. This seems hard. Like it kind of seemed hard to me at the beginning. I was like, how are we supposed to, incorporate a function with a dot and then look for the distance that is shortest? It's actually really, really simple, and it's all about Pythagoras again. There's the x here, there's a y here, we should say delta x or delta y. And we know that this point right here, really important to realize, is that it will give an x and the root x. Because root x is the y. Y equals to root x. Then when x is equal to x, y has to equal to root x. It's so dumb to repeat this, but that's basically what it means. If the function is equal to, well, they give you the function. Y is the function itself, so x, you'll get y, which is root of x in this case, because the function was a root x. And then you can use the distance between points, which is the Pythagoras. x2 minus x1 square plus y2 minus y1 square, and that's like the distance here. It's literally just Pythagoras dot squared plus dot squared. And here, instead of using x or y's, we have a 4, we have a 0, and then we have a x and the root of a x, and we just plug that in. Like that. I literally just plugged in the numbers x1, y1, x2, y2, and then we're going to distribute. It will become and then we can even factorize further. Yeah, so combining, and then that will turn into what we can derive at this point, deriving a root. Oh, I forgot to explain deriving a root in the previous video, but root basically means x to 2, so just product rule, x to the 1 over 2 minus 1, so that's going to give a minus 1 over 2, which is equal to 1 over 2 root of x. That's something I didn't cover in the first unit. So then we'll have x to 2 minus 7x plus 16. But then there's the chain rule. Whatever that's inside, we have to rewrite, but then their derivative form. So inside will be 2x minus 7. So that's the derived form of our relationship. Oh no. So this is our derived form of the rule, the fx that we found. For the fx, we turned it into f prime of x, and now it's time to set it equal to 0. By setting equal to 0, all we have to do is set the top equal to 0, because that's all that matters. So 2x equals to 7, x equals to 7 over 2, and that's the point. So the coordinate x equals to 7 divided by 2, so that's a bit less than 4, somewhere here, is when the distance from that, oh, never mind, I misread the question. So when the x is equal to 2, there is a dot somewhere on the function that is closest to the dot for 0. There could be many more. It could be like a question that is going from here to here and running from here to here type question. So here's lake, this is lake, this is water, and this is the shore. So this is grass, and that's a house right there, and you want to go from the boat. You're rowing a boat, and you want to go to the house. But then you row slower, and you can run faster. So then they will ask you from what for how long you will row, like a straight line, and for how long you will run, or long I should say, how long in distance. What's the distance you have to row? What's the distance you have to run? That type of question. It's all about, again, the distance. You're gonna look for a f of x function that will express the distance they have to cover, and you have to minimize the time. So you're gonna derive it to f of x, and that f of x you set it equal to 0, so that you're gonna look for the minimum and the maximum. And each time, I forgot to say it in the first few examples, but you have to prove that you found a maximum or that you found a minimum. That's really just plugging into the f prime function. To find whether you found a maximum or a minimum, plug it into the f prime function, a value a little bit before or after it. Let's say right now we found a 50 root. You want to find the y value of f prime of x with a x a little bit before root 50 and a little bit after root 50. Same here. A little bit before 7/2 and a little bit after 7/2 to make sure that you really did find a maximum or that you really did find a minimum. And if you found a maximum, it should go up and it should go down because the middle should be the highest. If you found a minimum, it should be going down and then go up after, so that the whatever in the middle you found is the minimum. And by up and down, it just means that the slope is positive or that the slope is negative. Same here. If the slope is negative and then the slope turns positive, then you know that you found a minimum. You found a maximum. And that's the same thing for the shore. You're going to look for a t function. Did I say distance function? It's a t function. So t function time is equal to the whatever distance that you will cover times the speed, because it will give you a speed 1 of rowing, speed 2 of rowing, and you know that v is equal to delta x over t. So t is equal to v times delta x. Using this, you will you will deduce or simplify to a function that expresses the t, how long you'll be rowing, how long you will be running, and then by minimizing that, which is turning into a derived function, and then set it equal to 0, you'll find the x value, which is this one. The x value for how long you should be rowing and how long you should be running. They will give you the shore distance, and they will also give you the length, distance. I'm just coming up with random stuff. And with Pythagore, you can find the distance from here to here, where x is what we're looking for. It's just going to be an expression. It's an algebraic expression for this line, the vertical diagonal line. And whatever that's left here is basically 3 minus x, right? You plug them in using this formula, look for the time, prime it or derive it, turn it into a 0, and you will find x. After you find x, you're going to have to look for the maximum or the minimum, or I should say to verify if it's a minimum or verify if it's a maximum. Same thing if it's going up and down, the slope is increasing or positive, slope is a negative, then you found a max, slope is negative, then turn it into a positive, then you found a minimum. Maximum, and that's I'd say they're all just following logic. Integration, yeah, so now we're finally getting into integration. Integration is the opposite of deriving. This is deriving. By going to the next prime, by adding more primes, you're just deriving. And it's the slope. It's the slope again. It's the slope again. So f prime of x is the slope of f of x. F prime prime of x is the slope of f prime of x. And f prime 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 is the slope of f prime prime. Same idea if you're going backwards. Use another color. If you're going backwards, it's the area instead of the slope, and you're doing the opposite, called the integration. Integrate. And that's the last unit for calculus. So integrating is always the area of the previous one. So the area of f prime of x is equal to the function of f of x. And that makes sense using some physics that you're supposed to learn along calculus. But let's say there's a position time graph that goes like this. Actually, that goes like this, and a velocity time graph. The area underneath is equal to the function itself, and the slope of the function is equal to the velocity time graph, where here will be f of x and this will be f prime of x. So going that way is area. The area here is equal to the function here, and going the other way, going this way, is the slope. The slope of this function is equal to the function of velocity. Now, that's basically all you have to know. You could add one more step here, which is, I'd say, actually really important in the integration, is that there is even a further integration to the original one. It looks like the original is the limit. It really isn't. It can actually go from the original backwards to the area of the original to the area. I don't know, we've never seen this before, but we usually stop at big F, capital Fx. And capital Fx is basically the area of original function. This is the original function. You can even further one step, finding or integrating the original function to get a capital Fx. Basically means the same thing from going from v to p. It's just integrating the function. But then a tricky, or like a interesting thing, it's not too tricky, thing is that if you derive this function that we just integrated, if you derive that, so if you do let's say g of x is equal to f of x, if you are looking for g of prime of x, it's basically the original function. Deriving an integral will give the original. That's called the fundamental theorem of calculus. And we somehow learned that at the very, very end of the calculus instead of the beginning. I think we should be talking about this at the beginning of integration. But if you have f of x, which is equal to g of x, and you're going to be priming that, we're going to be deriving that function, it will go back to the original function. And that's logic again, because this is the original function. You're going to be finding integration, and you do the derivation. Deriving an integration will give you original function, because just visually, that's what's happening. Integrating going up, deriving going down, so you're just coming back to it. So a notation, which is d on dx of, let's say, d on dx of another function, like this. So I should say a capital F in terms of dx will just give you f of x, where f of x actually will give you this. I should have just wrote f, normal f, because I didn't show you yet, but this one, this letter, this notation is the integration notation. A bit similar to like d on dx, but for the opposite, the contrary. Instead of deriving, we're looking for the integral, which is the opposite of deriving. When we do a big prolonged S shape with a dx, at the end, and we have a function f of x, this is looking for the integral of function f of x in terms of x. And in terms of x, something you have to know later on, but for now, you don't have to know too much about it. We're going to just go into the general rules already. So the general rules for integration is very similar to the derivation rules. It's just the first component integrated plus the second component integrated in terms of dx. Again, these are just meaning in terms of dx, a bit like we're deriving was related to x or in terms of x. If there's a constant, it's another rule. It's the exact same rule as the derivative rule. So it's just the constant times the integration. If there's a constant times a function, you can just do that constant times the integration of that function. So those are the two basic rules. There is another rule for integration, which is the inverse of power rule, or we should just say power rule, integration power rule. So if you have, no, not f, the integral of, let's say, x to the 8 d of x. I will just show you directly an example because that's, I think, easier. Normally, if it's deriving, you bring it to the forward, bring it to the front. So 8x to the 7 because 8 minus 1. So you do like a 8 minus 1 is equal to 7. You just have a new exponent called 7. That's the f prime of x. But when it is the integration, it's kind of you could maybe come up with it if you're really clever enough and you're a really bright student, but it's the same thing but opposite. You're gonna be doing x to the 8 plus 1, so that becomes a 9 divided by 9. Yep. And if you realize this turning into a derivative will give you x to the 8 again. So if I did x to the, if I derived this function instead, so that's basically 1 over 9 x to the 9. If I derived it, turn it into f prime, well, we have 9 over 9 x to the 8, where 9 over 9 basically cancels out, so it just gives the x to the 8, and that's true because that's the original one we got. So yeah, integration, you can kind of verify, you would check your work by doing derivative instead to find out if it gives the same thing. But if I tell you the actual rule, if there's a x to the m dx, what we have to do is x to the m plus 1 divided by x plus m plus 1 plus 1. That's the power rule. Exponent rule. The exponent rule is, there's only one. I mean, there's two actually. If it is a e to the x, I told you already in the second capsule, but e to the x deriving or integrating, going back and forth, will always give e to the x, and that is because ln of e is equal to 1. And you'll see why ln of e is equal to 1 will matter, but integrating e to the x dx will just give x e to the x, and you can prove that because if you derive e to the x, it gives e to the x, and you can do it infinite times, but it's just going to give e to the x always. Something that's not too obvious, or could be obvious if you're really clever, is when a to the x is instead of e to the x. So if it's a instead of a e, if there's a 3 to the x that you have to integrate, what we have to do is, I already wrote it down here, is the original, once again, the original function of a to the x times 1 over ln of a. So if it's a 3 to the x in terms of dx, it's going to be 3 to the x original times 1 over ln of 3. And again, you can check this work by doing the contrary for find the derivative instead. So the derivative will be 3 to the x, as per usual, times ln of 3, right? If you do it normally, if you derive this one normally. But then you also have a 1 over ln of 3. So if you have a 1 over ln of 3, and the ln of 3 will cancel out and give x to the 3, which is what we had originally. So again, they both work in terms of going back and forth. So you can prove yourself right. One thing though that you have to definitely be cautious of is when there is x to the minus 1. When there's an x to the minus 1, you realize that by adding 1, like we usually do, it gives it 0. So it's going to give an x to 0. But that's not true. Let's say an example, f 3 x to the minus 1 dx equals to what? You can't just apply the normal rule of going like x equals to minus 1 plus 1 divided by minus 1 plus 1, because then you're doing like a 3x to 0 divided by 0, which makes no sense. That does not work. So instead, what you have to do is to remember that, first of all, x to the minus 1 means 1 over x dx. And 1 over x, if you remember from deriving, is the derivative of ln of x. But be careful, because ln of x, you can either be a negative or a positive ln. And there is also a proof to that, but basically if there is a negative inside a ln, it does not exist. So you'd have to turn it into a negative. There is a whole explanation or a whole demonstration you can do about it, but just remember, every time that you see 1 over x that needs to be integrated, just write ln x in absolute value, so absolute value x. So this one will just become 3 times ln of absolute value of x. And 3 is a constant k, that's a k, 3 is a k, so k just sticks around. And 1 over x turns into a ln of absolute value of x. And to find out why it is of absolute value of x, well, the simplest reason is that ln inside of a ln cannot be negative, so you have to turn it into the absolute value, but there is proofs to it. Again, proofs that you don't have to know. Lastly, we have the trig rules for integration. And these are exactly the same thing as deriving, just the other way around. But it's not everything that we know for trig. There are 6 that you have to know. 4, 5, 6. There's 6 that you have to know. They are that of cos of x, sine of x, secant to the 2, and cosecant to the 2, secant tangent, cosecant cotangent is equal to. And they are actually just the reverse of everything. Oh, I think I forgot to mention something. Okay, I completely forgot to mention something. You have to always write a plus c. Always write a plus c after you do your integration. And that is because whatever constant that was in the original function will disappear once derived. So when you go from integral, so integration, so when you go from the derived form into the original form, you have to add a plus c. And I mean c. It's not algebra here. It's c. You really have to write c every time. It just means constant. Because remember how 3x to 2 plus 4, for example, when you derive it, it just becomes 6x. And the 4 just disappears completely, but it doesn't mean that it doesn't exist. So in a function, if you're integrating and it's indefinite integral means there's no bounds. I'll talk about what that means, but if it is indefinite, and all of these are just indefinite, if they're just telling you to turn this expression into a derived, into its original form, so integrate the expression, it's always indefinite form. If they're asking for area between, because remember how integration is area, if they're asking what is the area between from here to here of x1 and x2, that's a bounded area, so that's indefinite form. This one is, that's a definite form. So finding an area between this region is a definite form. This one is an indefinite form, so indefinite integration, always add a c. So here, where we integrate cos or sine or secant or cosecant, we just turn it into whatever they were supposed to be originally, plus a c. Here, there's a minus cos of x, because remember, whatever cos function turned into their derived form will have to have a negative. But if it didn't have a negative in the derived form, you have to put it into the original form. And it's just vice versa kind of question. This is tan. This is minus cotangent x plus c. Because when you integrate cotangent, it becomes negative cosecant square. But right now we don't have a negative on the cosecant square, so we just need it on the other side. Plus a c, secant x plus another c, and negative cosecant x plus c. And these you can prove once again from going the other way around. Because remember, sine of x turns into a cos of x. Cos of x turns into a negative sine of x, so then negative cos of x turns into a sine of x. Same thing for tangent. Tangent turns into a secant to the square. That's what we wrote. Cotangent turns into a negative cosecant square. And since cosecant square doesn't have a negative, so we can say that negative cotangent turns into a cosecant square, positive cosecant square, etc. But these are just memorization, once again. Just need to memorize this. But if you memorize the derivatives, I'd say that it's really easy to remember the integrals. And these 6 are all you need to know, at least at John Abbott. And there are the inverse trigs. I lied, there's inverse trigs, not everything you need to know. There's 3 more you have to know. Actually, 2 more. Integrating 1 over 1 minus x squared. This should be familiar. This is the arc sine. So that's just arc sine of x plus c. Always don't forget your plus c. Integrating 1 over 1 plus x squared in terms of dx is arc tan of x plus c. Don't forget the c. And there is no arc cos. And that is because arc cos is just a negative of that. So if you see a negative, you can just put a negative arc cos, arc sine, sorry. Just need to add a negative if it is a negative. I think it's not wrong to write arc cos. So instead, if it was a positive, you have to go like negative arc cos or positive arc cos instead of positive or negative arc sine. They kind of give the same thing because as long as you're consistent with the signs, they're both acceptable. But in our case, we just answered arc sine. And what's tricky here is that sometimes they will mix it up and make it look weird, like 4 minus 4x to 2. They will tell you to derive this, and it doesn't look familiar unless you can know to factor. If you factor this, it will be a 2. You can take the 2 out, and it will be a 1 minus x to 2. And then even more clearly, that's a minus 4 over 2, and 1 over 1 minus x to 2. So tada, you have an arc sine here now, if you derive that. And deriving that, well, it's just a constant, so it just comes along. So it's minus 2 times arc sine of x. And that's the answer. Otherwise, if you see a negative constant, well, just, if the constant was negative, just applies everywhere, because constant, negative or positive, doesn't matter, just sticks around everywhere. And integration, you can do just a whole bunch of exercise of straight up integrating. It can be as weird and as long as the question may be. All of that integrated will give. So that is, well, first we want to rewrite it actually. This one we want to rewrite it because that's a 3 over 4. And that's a negative 10 times x to the 8 over 5, but negative because it's under, it's in the denominator, plus 12. And don't forget your notations all the time. X to the 6 divided by 6 plus x to the 3 on 4 plus 1 is just plus 4 on 4. So that's a 7 on 4 divided by 7. Oh, sorry, that was not a 4. That was a constant. That was a constant 4 times x to the, so that's x to the 1 over 3, sorry. So that's a x to the, so 1 on 3 plus 3 on 3 instead is a 4 on 3 divided by a 4. Oh, no. It's actually x to the 3 on 2. Yeah, because it's a root. I was mixing up the fourth root. So that's the second root because root is always 1 over 2. This is equal to 1 over 2. So then if there's a x to the 3, then it's just x to the 3 over 2. So now we do 2 over 2. So you add 2 over 2 because that's adding 1. That will give 5 over 2 divided by 5 over 2 minus 10 times x to the, well, minus 8 over 5 plus 5 over 5 will just give minus 3 over 5 divided by minus 3 over 5 plus 12x. So I kind of didn't talk about the constants. Whenever you see a constant like 12, just add x to it. And that makes sense because if you do the other way around, 12x, you derive 12x will give a 12. If you don't know why, you should watch the derivatives video. And then we add a c per usual, because it is an indefinite bound. And you can definitely simplify this. You can simplify 3 on 6 to x to 6 on 2. And this one can be multiplied 4 times 2 on 5, x to the 5 over 2 instead. And this can be even further simplified to 8 over 5. Plus, so 3 over 5 is divided, so 50 over 3, x to the minus 3 over 5, plus 12x plus c is a further simplified answer. Some stuff you should be careful about. 3 pi to the x. If you derive this, you have to realize that, well, pi to the x is the exponent. So it has to be pi as 3 times, well, 3 is a constant, pi to the x divided by ln of pi, for example. Doesn't look so familiar, but that's applying the real rule. And even more confusing, or not, maybe not confusing. 3x to the pi, well, that is like x to the a, or x to the 2, or x to the 9, or anything. In this case, it's just 3x to the pi plus 1. It's so weird to see that, but it's actually pi plus 1, because the pi could have been a 2, could be a 3, could be a any number, any expression, algebraically. It's gonna be a pi plus 1 divided by pi plus 1 as well. So yeah, integrating, not deriving. Integrating 3x to the pi is 3x to the pi plus 1 divided by pi plus 1. And another common mistake I see is like, or the teacher tells us that we see because they don't correct anything, but 3 pi is a constant. Lots of people kind of mix up with the pi and they go like, okay, it's like a pi to the 1, I don't know, maybe maybe turning it just into, I honestly don't know what the mistake could be, but 3 pi is like 3 times 3.14, so it's gonna be like a 9.14, let's say. And if you see a 9.14 and deriving that, integrating that will just be 9.14x, right? So the same thing here for the 3 pi will just turn into a 3 pi x. Like I said, integrating 1 over x turns into a ln of root x, and so that's it for indeterminate. Well, indefinite, indeterminate. I think it's indeterminate integration. If it's a determinate integration, I'm not sure if that's the real name. Basically, let's say you have a. That's too complicated. You have, basically it's a closed bound. It's when there is a function and they will tell you the first x and the second x, and you're looking for the area in here, because when you're doing normal integration, you're finding the new function. It's like an entire function that is the area, or that was whatever. If it was a derivative, it's gonna be the original function of that derivative function, but it's the area function of the previous one. So you can do the area function of the entire previous one. So in this case, it will look like that. So that's the area. The area is gonna, well, this area will turn into that one, that one will be slope. It's like a slope area relationship. But instead of finding the entire function turned into integral, we can look for the section, a specific section, and that's basically looking for an area from the given 2 points, and that will be written as a to b of f of x dx, where a is this one, b is this one, and yes, we put the b on the top. This notation could be given example as, let's say, pi over 6 and pi over 2 of cos of x dx. What we have to do is first integrate. So cos of x turns into a sine of x plus c, but you don't need to add plus c for definite integrals. They're definite integrals because, well, you'll see, but the whole point of doing this is to find the area from here to here, take away here to here, so that you end up with the wanted area inside here. And to do that, we have to do a subtraction of the integral. So let's say that you added the c. The subtraction is all about plugging in the top one, taking away the same thing function, but plugging in the second one. So you have to take away. And the takeaway action comes from finding the area of everything from the x2 and below by the x1 and below. And if you subtract that one out, you would just be left with whatever that's red in here. That's what we want. That's why we're subtracting. But then if we have a plus c, take away another plus c, well, c minus c just becomes 0, so you don't need to care about c's. So when it is a definite integral, you don't need to care about the constant c, the c constant. Oh, that does not erase. So that's what we're going to be doing. That's not the final answer though. We will have to just plug in, knowing your trigs. So sine of pi over 2 is 1. Take away, well, the sine of pi over 6. So sine of pi over 6 is here. That's a 1/2. So 1 take away 1/2 is 1/2. And there's nothing you have to do with c's or anything like that. Let's do another one. 0 to 2 of 1 plus x2 dx. That is the arctan, if you realize. So arctan of x from bounds 1 to 0. That means, well, arctan function looks like this. So we want from 1 to 0 the area under the curve. So this area is what we're looking for. So then we have arctan 1, take away arctan 0. And again, you just need to plug in. But arctan, if you forgot, arctan 1 is equal to theta, set it equal to theta, because 1 is equal to tangent of that theta. So now you just need to look for a tangent. Well, you just need to look for an angle where tangent of that angle will give 0. So in that case, it's going to be a pi over 4. Pi over 4 has like root 2 over 2, root 2 over 2, and just dividing that will give 1. So the first tangent, or the first theta, is equals to pi over 4. And we do the same thing, but when arctan is equal to 0. So now 0 equals to arctan. So that is when basically the top has to be 0. So if the top is 0, sine is 0. So this one will be, you can say they're 2 pi, but usually would say 0. Arctan of 0 will have coordinates 1 and 0. So arctan sine over cos 0 over 1 will give 0. So minus 0. So arctan of 0 is 0. Arctan of 1 is pi over 4. We do their subtraction. That's just going to give pi over 4. That's the answer. There is not much more to it, but if you were to find a question like this, you were to find a question like this, you just straight up say 0. If you want to show work, you can show it like this, meaning big F meaning the integral, so it's already integrated, and just write 2, 2. If you plug that in, well, that's just the same value, take away the same value, so the gap is at 0, so the answer is 0. What is this showing graphically? Let's say there's a graph that's 2, and that's 2 again. There's 2's and another 2. I'm trying to find the area between the curve of 2 and 2, like the area under the curve of 2 and 2. Well, there's no such area, because it just doesn't exist. The space in between a 2 and a 2 is nothing. That does not exist. So the area, well, the area it's not D and E, does not turn into a D and E, it's just 0. Just write 0. And it could be tricky because sometimes the teacher will go like, okay, this one, if you rationalize it, it will turn into 2 over 2, 2 over root 2. So then they will show you, oh, 2 over root 2, and root 2 over 2, please. That's actually the same thing, if you don't realize. That's the same thing. So some student kind of tripped saying that, oh, we're trying to find out root 2 over 2 plugged in, take away root 2 plugged to, take away 2 over root 2, and they just never get to an answer. But if you see that something's weird and you can't solve, most likely the answer is supposed to be 0 and you're not supposed to do any calculations. And that happens often in calculus. If the answer just does not exist, or if it's just not possible to calculate, the answer is just no solution, or D&E. And that in that case, you have to just come up with the solution and not do or show any work. Something else that could be worth talking about. Let's say there is a bound 0 to 7. Bound 0 to 7, it's kind of annoying to write f of x dx every time, but it's the same thing as 0 to 1 plus 1 to 5, let's say, plus 5 to 7, f of x of dx, f of x dx. And that is also, again, visually possible to see. That's it. That's 0, that's 1, that's 5, and that's 7, let's say. The area from 0 to 1 plus the area from 1 to 5 plus the area from 5 to 7 is equal to the area from 0 to 7. That's logic, right? Yeah, like calculus is basically logic. That's helpful because sometimes they'll give you, let's say, bounds from 7 to 5 of 3 times f of x dx is equal to 4, let's say. To go from here to this is possible. It's totally possible. You just need to memorize or remember a few concepts. 5 to 7 turned into 7 to 5 is the negative of it. So first off, let me just rewrite this. Equals to 4. We want to turn this into this blue thing right here. We want to turn that into that. First, do 5 to the 7 instead of 7 to the 5. And the 4 becomes negative. From here to here versus from here to here, it's just a difference of sign. Turns into a negative instead. So now we have 5 to 7, which is the bound we want, 5 to 7. And we have a 3 here, so we want to divide it on the other side, because remember that 3 can be taken out. Can be taken out to the front. If you can take it out, you can also divide it on the other side. So we have 5 to the 7, f of x dx is equals to minus 4 divided by 3. And you have 5 to the 7 already. So you know the area here. Right now it's negative 4 and 3, although it should be positive. This is just a random example I gave. It should be positive. So the positive or negative depends on if it's on the top or the bottom of the axis. I'm just going over everything in like one breathe. But if the area, if the curve is on top of the area, the axis, the area is always positive. But if the curve is under the axis like this, the area here is going to be a negative value. It's actually going to be a negative value. Not only that we represent it negatively, it is a negative value. And then the whole concept of 0 to 1, 1 to 5, 5 to 7 added together is just showing over here. Something else we need to know is to find the area in terms of shapes, in terms of geometry, in terms of, I should say, in terms of area. Just finding the integral in terms of area. And that's really obvious if it's like a really pointy, very geometric. You don't even need this line 5, let's say, and they tell you that's a 4. So if they're telling you integral from 0 to 5 of the function dx, you just need to calculate the area here geometrically. You don't even need to do calculus, and they'll give you the right answer. And sometimes they do tell you to use the geometry, the area on the picture on the graph. Something else you need to know is the circle. And the circle, it looks like this. It's kind of similar to Pythagore. But if you have the radius squared, actually that's not the right answer. It's actually y equals to root of r squared minus, yeah, it's a negative sign, it's a minus sign. So if you have the y coordinate and the x coordinate, well, squared, because you have originally that, so I think that's the right answer. Yeah. So x squared plus y squared instead of, y squared equals to x squared plus r squared. This is the original function of the square, but turned into this format and given to you as a integral. Let's say 16 minus x to 2 dx. You have to realize that this is a circle. And it will be either a semicircle or a quarter circle, but in our case, let's say minus 4 to 0, so that's a quarter circle. Because that means it's a circle where the r is equal to 4, right? Because root of 16 is 4. This is minus 4, this is 0. And the area from minus 4 to 0, but that has to be above the axis. It's right over here. And we know that it is above the axis because there's a plus or minus here, actually. By doing the root of y, actually. The root of y should give a plus or minus. And since there is nothing indicated in at the front, it will be a plus. Plus meaning it's an area on top of the curve. So it's an area on top of the axis, which is a positive area. And again, that is just pi r to the 2 divided by 4, where you know the r. So we have, or I should just do integral of minus 4 to x minus 7 dx is equal to, in our case, 4 pi, because we know that it's just a quarter of the circle and r is equal to 4 in our case. One more thing for integration is two functions where we're looking for the area in between the two functions. And that is from, the A means the area. This formula, or not a formula, but concept. So it's the integral from A to B, A and B being the point of contact, of y upper, so function, the upper function minus the lower function. And that, again, is a common sense, or not a common sense maybe, but a logic. Because if there's an area under the curve for the first function, that's all of this. Take away the area under the curve of all of, the area under the curve of the upper function, take away the area under the curve of the lower function, it will result visually in this function, this area over here, even just by drawing it. Simpler one, let's say we have a two functions like this. If you want to know the function, the area in between from the two functions of this region here, we first have the upper function, its area, so it's total area right here. Take away the lower function area. So what happens if we take that away? Whatever that's left is the red region. Same thing over here. Whatever that's here on the top on top of the axis, that is subtracting from the area on top of the axis of this function. Well, the remainder is this shape inside, in between, stuck in between. And this is really, really simple to do for, let's say, an example of 2x minus x to 2. That's the first function. Take away x to 2 plus 4x is the second function. All of that dx. All we need to do is to, well, first of all, integrate. So, actually, no, sorry. Before you integrate, you can just simplify. Simplify meaning you're doing the subtraction. You're doing the subtraction, so forget about the integration, just subtract. You will have minus 1 to the 2, minus 2x to the 2 minus 2x dx. Yeah. And all of that integrated, so that will become minus 2x to the 3 over 3 minus 2x to 2 over 2, which simplifies to just x to 2. Bounds 0 to 1. So that just means there's a function that looks like this. It's from bounds 0 to 1, so 0 to 1, 1 be the contact point. Now, if the 1 wasn't the contact point, if 1 was here, let's say, you'd have to look for, actually, this is not a really nice drawing, but let's say if it was like this, this is something important you have to know. Let's say you're looking for 0 to 1. This is a transition case, because at the beginning, from, let's say this is 0.2. From 0 to 0.2, the area in between, the top bound is this one, the upper, and the bottom one is this one. The area in between, you have to do the top minus bottom. But then over here, all this region, it's the opposite. This one is the upper one, which was originally the lower one. And now this one is the bottom one, which it used to be the top function. But you still have to follow what is on the top and what is on the bottom. So what you have to do in this kind of case is go from 0 to 0.2 and then do the upper minus lower, plus from 0.2 to 1 of upper minus lower, same concept. And that will work because that's like the theorem that we kind of looked at the beginning, a few while ago. 0 to 0.2 plus 0.2 to 1 is the same thing as 0 to 1, but specifically we're only talking about the regions that we want really specifically. So the upper function take away the bottom function. Always look at the diagram or the drawing. And here we just need to plug in. So plug in each x and you get an expression. Take away plugging in each of these expression, and that is supposed to give 1 over 3. So Riemann sums is all about repeating shapes infinite amount of times. So the first concept is many rectangles. There is two types of rectangles. There is the right endpoints, there's the left endpoints, and actually there's three types. There's also the middle endpoints, but it's really not a big concept you need to know. it's also really quite childish. I don't know. There is points at each section, right? Like 1 to 2 or 5. And basically, for finding the area under curve, instead of doing integrals, we can do shapes. So if you do a right endpoint, the right endpoint, we're just going to prolong the lines of the y value found that x value, and just prolong those lines. Just prolong those lines from the right side. And we're going to add those areas. We're going to add those areas together to find the approximate area under the curve of a curve, the area under a curve. This is the right endpoint. If it's the left endpoint, it's the same thing, just using the left side points. So let's say that's 1, 2, 3, 4, 5. You take the left endpoint. So no. So left endpoint will turn out to become the left one to 1. So left one, another left one, another left one. Actually, it's here. It's here. Oh, I totally messed it up. Either way, the whole point is to find the y value. Find the y value at the given x, and from the left of x to the right, I'm going to draw a rectangle for left endpoints. And from the x to the right, if you're trying to look for right endpoints. And it's just building so many rectangles like this to make an approximation of a curve area, where it could be more, it could be overly estimated or underly estimated depending on how your rectangles look compared to the graphs. And that's all Riemann sums is about. And that's the geometrical, or I should say the area drawing type Riemann sums. There's another Riemann sums concept you have to know, which is a lot more important, called the limits of Riemann sums. I'm not gonna lie, my throat is hurting from talking for like 3 hours straight already doing these capsules. So definition of derivatives, definite integrals, in the limits of Riemann sums, it's just straightforwardly limit as n approaches infinity of sigma n I equals to 1 of f of xi times delta x. That's the formula. You have to memorize this, where delta x equals b minus a over n, and where xi equals to a plus I times delta x, and delta x is b minus a over n. It's the same delta x. What this is doing here is the same concept as the rectangles that we just saw, but making these rectangles infinitely small. And that's it, because n is the number of rectangles, and delta x is the width. Delta x is the width of the rectangle. This is like delta x. That's why delta x is equal to b minus a divided by n, because that's b, that's a, so b minus a is the length from b to a, from a to b, and you divide it by the number of rectangles will obviously give you the length, which is delta x, the length, or the width of your rectangle. And by making your n approach infinity using limits, you're basically making infinite amount of rectangles. And by making infinite amount of rectangles, the rectangles are going to be so precise to compared to the related to the function, the curve. So then the area is going to be infinitely precise to the point that's perfectly precise. And that's done by math and calculus. So now if the number approaches infinity, this notation here just basically saying repeating this process from I equals 1 to n, where n is infinity. So we're being told that n is approaching infinity. We're going to repeat this process for infinite times. But it's actually not too complicated to do that. We're going to be given a f of x, which represents this function, f of x. And they're going to tell you what is the limits of Riemann's sums using the definition of limits of derivatives of definite integrals, not derivatives of definite integrals. Just going to do one example. But before that, I want to write down that there are a few things you need to know that are usually given, but some formulas. I personally memorized it, but you don't have to. It's just for you to be sure and not make silly mistakes or transcription mistakes. But if you could, you should memorize these. All of that squared. So these are some stuff you need to memorize. Or actually, no, you don't need to memorize, but it's just handy because we have to use them later on. So the whole point of Riemann's sums with this notation, this weird notation with a lot of signs on it, they're going to give you a function f of x. Let's say f of x is x to the 3 minus 3, x to 2 minus 2. So we know that we have to do, actually first step by step, delta x is equal to b minus a over n. So they're going to tell you the b and a. And in this case, we had a b of 3 and a of 0. And a's are usually always going to be 0, at least for cal 1. Divided by n, which is the infinity, but we just write it as 3 over n. Now we have xi, which is equal to a plus I delta x, where a is 0, so it's just equal to 3i over n. Just added an I to it, you know, multiplication. And now we have everything we need. Just remember, because we're not going to have space, that delta x is 3 over n and xi is 3i over n. F of xi as an approach infinity of sigma n I equals to 1 of f of xi, so the f of xy will turn into 3 xy was 3i, 3 ni or 3in to the 3 minus 3 times 3 over ni, actually 3i over n and 3i over n to the 2 minus 2 times delta x, so the delta x was 3 over n. Just focus on first distributing these, so then you're gonna get you can do your cubes and the squares as well. To 3 over n to the 4 minus 81 I to the 2 over n to the 3 equals to n, no, minus 6 over n. So all I did was just distribute 3 over n to each component, and for each of their powers, we're going to apply their powers. From here, it's a bit new. Well, we're actually just distributing once again, but instead of normally distributing, we're going to take out the constants and leave the I to the something. I to the something, I to the something, we want to leave that with distributing the sigma and the ny notation. So again, I stays, everything else we take it out, everything else we take it out. So right now we have a 1 here because n 6 over n, there's no I, but technically there's just 0I, we could just leave a 1 here. We're supposed to leave a 1 there. And now as n approach infinity, this comes from the limits rule, but they will cancel out because they will divide by a very, very, very big number. And by dividing a very, very big number, we just end up with the biggest coefficient with the biggest denominator's power, with the biggest power. It was referred to the denominators. So in this case, we have n to the 4 times, remember the notations here, these notations that you have to memorize, I to the 3, I to the 2, I to the 1. Right now we have I to the 3, so that becomes n plus 1 over 2 all squared. Again, this is just rewriting. I to the 2 is n plus 1, 2n plus 1 divided by 6. And take away 6 over n times just n, because n as I approach 1 of n is just n. Just remember that gives an n. And still there's a limit because we didn't evaluate the limit yet. And now we evaluate the limit. We're going to distribute the 2's. Don't forget to distribute it here. That turns into a 4. That turns into a 4 instead. That becomes 81 over 4 minus 81 times 2, but then divided by 6. So just do divided by 3. So 81 divided by 3. And then minus 6, but then the ends are canceled out. So minus 6. So that simplifies to 81 over 4 minus 33. If that's right. Yeah, that's right. So that gives 81 over 4 minus 33. And we don't have a calculator in exams, so most of the time they should tell us that we are allowed to have, most of the time we're allowed to not simplify to the most perfect answer. So that's like basically everything for calculus in the first year. There is the fundamental theorem of calculus and some question related to that, but as long as you understand this concept of going up and down, every time being slope, area, slope, area, area, slope, and they will tell you if g of x is equal to integral of f of x, what is g prime of x? And the answer is just f of x, because f of x was the integral. So it basically means the original function that became integrated. If you do a derivative of that function, just goes back to the original function. So just that guy remains. And whatever integral notation will go away. There is the velocity, displacement, and acceleration unit I didn't cover, but it's really the same concept as here. This is the displacement. So let's say displacement is p. Displacement, velocity, acceleration. These trio, you have to understand that it's the prime of each other and the integral of each other. Don't mix up which one's what. Usually on Earth, it would look like this for acceleration, velocity, and the position. One thing you definitely need to know is this one. They will tell you they will ask you what is the distance that was covered, what is the total distance, and what is the displacement. So the word displacement and the distance, or the total distance, talks about completely different stuff. And that is because if the person was walking forward and then stopped, and then started walking backward and went back to its original position, the displacement is 0. What that looks like on the graph, especially on the velocity graph, is something like this. And that will be, well, that kind of doesn't exist as of time because there's no negative time, but let's say it's like this. Okay, time is 0. There is a negative area that they walked, and then there's a positive area. Actually, that should be the opposite. Should be the opposite. All of that should be the opposite. Let's say it's like this. That's more realistic. There is a positive area that they walked forward, and there's a negative area that they walked backward. That will add up together, which is the 0 to 5. Let's say that this is 5. That they went that way 2.5 seconds and went back that way 2.5 seconds. The total displacement is equal to 0, but the total distance that they walked, the total distance, is the total area, so you have to add them. Whereas displacement, you add if it's above axis, and subtract if it's under the axis, which is the case here. So then what you have to do is subtract here. This one, take away this one, will give you 0, which is normal if you walked from point 1 to point B, and from point B to point 1, just came back, the total displacement is 0. So the whole tricky part is to not mix up with the bounds. If they walked to a certain point, that's 2.5 seconds, you have to do 2.5. Actually, if you were looking for the total distance, you have to do 2.5 plus 2.5, of course, your function, dx, and that is your total displacement. Distance covered, but not your displacement. Displacement would just be 0 to 5. It's the most easiest. You don't need to care about if it's positive or negative, if it's going forward or backwards, on top or bottom of your axis. Just do 0 to 5, because the area from 0 to 5, they will automatically, when you do the calculation, when you plug in the values, they will automatically give you the total accumulated area and not the total added absolute value of the area. So the accumulation of area is going up here and it's decreasing here. The area is decreasing. So then whatever you end up with from 0 to 5 is the displacement, not the total distance. And yeah, other than that, just going back and forth with integration and derivatives. And that's it for calculus. So you covered everything you need to know for Cal 1 for John Abbott College, Unit 1, 2, and 3 if you watched the 3 capsule videos.